on this channel. So essentially everything you see in the live streams, being developed in the live streams, is available on BioniChaos.com. So yeah, let me know if you want me to talk about any of the tools. Yes, they were developed by AI. And yes, I should know how they work. So I'm happy to jump into any examples. Especially you can just check out the tools yourself. Let me know which one you like best. And we have quite a few more web applications coming. So they're all interactive web applications. We're trying to avoid static pages. If the page is static, it's only because the interactive component didn't work. So we do have a Hodgkin-Huxley. Can you explain real quick what's happening on the screen?
On the screen, we're observing a simulation of the Hodgkin-Huxley action potential. This is a model that describes how neurons generate electrical impulses. The graph at the top shows the membrane potential over time. You can see the voltage changing, and it looks like a stimulus is active, causing the membrane potential to rise rapidly, which indicates an action potential is firing. Below the graph, there are representations of sodium and potassium ion channels, showing the current of these ions.
Okay, can you read out this question? I'll just scroll through the response. Can you just summarize the response for me real quick?
The Hodgkin-Huxley model is a detailed conductance-based model that uses nonlinear differential equations to describe ion channel behavior in neurons. Other neuron simulations might simplify these details, focusing on overall membrane potential dynamics, or use stochastic models for individual ion channel behavior. It is deterministic, and its framework allows for detailed multi-compartment neuron models and various synaptic inputs.
Hey, can you read out the questions, related questions?
Certainly, the related questions are, how does the Hodgkin-Huxley model incorporate ion channel dynamics compared to others? What role does stochastic channel behavior play in the Hodgkin-Huxley model's predictions? Why are some neuron models based on thermodynamic principles instead of ion conductance? And in what ways do Markovian models differ from Hodgkin-Huxley's conductance-based approach?
Can you read out or summarize in detail the highlighted text?
The highlighted text states that the Hodgkin-Huxley action potential simulation tool visually demonstrates the dynamics of neuronal membrane potential during an action potential using the original Hodgkin-Huxley mathematical model from 1952. Its key features include accurate biophysical modeling of sodium and potassium ion channels through 4 nonlinear differential equations, real-time visualization of membrane voltage, ion currents, and gating variables, use of high-precision Runge-Kutta numerical methods for stable and accurate solving of equations, interactive stimulus input to observe how stimulus strength affects action potential generation, and a demo mode to illustrate fundamental neuron concepts.
Can you read the highlighted text?
The highlighted text states, this simulation captures classic Hodgkin-Huxley results with over 98% accuracy for the squid giant axon at 6.3 degrees Celsius, making it a valuable tool for understanding the foundational neurophysiology of action potentials and neuronal excitability.
Okay, can you explain real quick why after some time when we applying a stimulus, the neuron would not fire based on what you see on the screen? Can you actually turn it into a question, rephrase it into a question?
Considering what's displayed, why does the neuron fire even when a stimulus is applied?
Now, can you expand the question, make it specific to the web application, make it elaborate but standalone?
Given that the stimulus is active, why is the neuron not firing in this Hodgkin-Huxley action potential simulation?
Now, can you expand on it? So it's firing the first time around, but then there is the time delay. Can you for it to fire again? Can you include it in the question? Elaborate on that. Turn it into a question.
After firing once, why is there a time delay before the neuron fires again in this Hodgkin-Huxley action potential simulation, despite the stimulus remaining active?
Okay, can you read out the response?
After the neuron fires once in the Hodgkin-Huxley action potential simulation, there is a time delay before it can fire again, despite continuous stimulus due to the refractory period of the neuron. This period arises from the biophysical properties of the ion channels. The absolute refractory period is immediately after an action potential, where sodium channels become inactivated and no sodium influx can occur, preventing another spike. The relative refractory period follows, where sodium channels begin to recover, but potassium channels remain open longer, hyperpolarizing the membrane. A stronger than normal stimulus is needed to trigger another action potential. This refractory behavior is due to time-dependent gating kinetics of the sodium and potassium channels, which control their opening and closing and require time to reset.
Okay, do you have any interesting questions about this?
Yes, I have a question about the graph. It shows two action potentials. Why is the second action potential lower in amplitude and broader than the first?
Now, do you know the answer to the previous question?
Yes, the reason the second action potential is lower in amplitude and broader than the first is due to the phenomenon of the relative refractory period. During this period, some of the potassium channels are still open, and some sodium channels are still inactivated, making it harder to depolarize the membrane to the threshold, which leads to a smaller and slower action potential.
What are the two channels called again?
The two channels displayed are sodium, denoted as Na+, and potassium, denoted as K+.
So what's the difference between them?
The key difference lies in their roles during an action potential. Sodium channels, Na+, are primarily responsible for the rapid depolarization phase where the neuron's membrane potential becomes positive. Potassium channels, K+, are mainly involved in the repolarization and hyperpolarization phases, bringing the membrane potential back to its resting state and briefly making it more negative.
Can you turn it into a question asking to explain this in plain language?
What are the roles of the sodium and potassium channels in generating an action potential in the Hodgkin-Huxley model?
Explain this in plain language without any terminology. Can you summarize the question real quick and then read out the response?
The question asks, what are the roles of the sodium and potassium channels in generating an action potential in the Hodgkin-Huxley model? Explain this in plain language without any terminology. The response states, in plain language, the roles of the sodium and potassium channels in creating an action potential in the Hodgkin-Huxley model are: when a neuron gets a signal strong enough to activate it, special gates for sodium open, letting sodium ions rush inside. This makes the inside of the neuron more positive very quickly, like a sudden burst of electricity. This is the spark that starts the nerve signal. After a short moment, the sodium gates close and gates for potassium open. Potassium ions then flow out of the neuron. This outflow helps return the inside of the neuron to a more negative state, like resetting the electricity back to its resting level. This cycle of sodium rushing in, making the inside positive, and potassium rushing out, making it negative again, creates the spike in electrical charge called the action potential, which travels along the neuron to send messages. Importantly, these gates open and close at different times in a controlled sequence, so the signal is a quick, one-directional pulse rather than a continuous current. Simply put, sodium channels let positive charges rush in to start the signal, and potassium channels let positive charges flow out to reset the neuron so it's ready for the next signal.
And yes, everything we do is available on BioniChaos.com. Go check out the website, let us know what you think. But the questions and the comments have to be relevant to a specific tool or video. Okay, this is something else. It's still prototyping.